Hello, everyone. This is the lecture for section 4.10, antiderivatives. So this section will not be on exam 2. I'm going to push this off toward the final. Okay, so you can go ahead and push this section off if you need to study up for this for exam 2. Okay, and there's a reason why I'm pushing it off to the final instead of making you guys do this for exam 2. It has much more to do with, I believe, with chapter 5 material rather than chapter 4 material. Though it is sort of, it does have chapter 4 material in there. It's got much more chapter 5 stuff, I think. So I'm going to go ahead. That's the reason why I want to push it on to chapter to the final. Okay. So what chapter 4 or section 410 is going to start doing is it's going to get us into what you guys are going to be studying in Calc 2 once you get there. Okay. And that is the integral. Okay. So in Calc 1, what we do is, and this is by and large, you know, in any Calc 1 class that you take, Calc 1 does just the derivative with a little bit of integration, and then Calc 2 takes care of the rest of integration, takes care of the rest of an integral. Okay, so that's what we're going to be doing here. We're going to get you started on stuff for Calc 2. Okay, so we're going to start looking at what's called an integral in chapter 5. But before we look at an integral, we're going to start looking at this thing right here. It's called an antiderivative, and it's exactly how it sounds. It's anti a derivative. So whatever the derivative did, right, the antiderivative undoes it. Okay. So what we're going to see in a bit once we get into chapter 5 is that an integral and a derivative sort of undo each other, but that's for later. Okay, I don't want to spoil the finale there. Okay. First thing I want to define, right, is the definition of an antiderivative, okay? A function big F. So now I have to define a big F as opposed to a little f, right? A function big F is an antiderivative of a function little f, if this is true. If I can take the derivative of big F and get little f back for all the values in the domain of f. Okay, so how does this actually work out? Let's go ahead and scroll down to the first example here. Okay, so consider the functions, those two right there, big F, that, and big G, that. Okay, and those are supposed to be big F and big G. It's supposed to be big G. Okay, so both big F and big G are antiderivatives of what common function? So if we go ahead and just take f, big F prime of x, right, we can see that this is going to be 4x plus 3, right? And then if we take g prime, big G prime of x, that's also going to be 4x plus 3, right? So my little f of x is 4x plus 3. So that means that both of these functions, right? So big F, right, and big G let me finish writing it. Okay. Both big F and big G are antiderivatives of this little f, 4x plus 3. Okay. So how do they differ? So looking at big F and looking at big G, what's the only difference behind them, right? Big F of x, right, has a plus 18 at the end, right? And big G, right, has a minus 3 at the end. That's the only thing that's different, right? That is, if you take a look at the front portion, they both have the same front portion right here. It's a 2x squared plus 3x for both of them, right? The only thing that's different in the first one, it's a plus 18, and in the other one, right, it's a minus 3. There's your difference, right? So looking at just that, right, Can we find some more? Just looking at that language, just looking at that difference there, can we find some more big F's and big G's, right, that are antiderivatives to my f of x, my little f of x? And the answer is yes. It doesn't matter what we put down, right? So long as that front portion is that 2x squared plus 3, the tail can be whatever it wants. So for example, right, big f of x can be just 2x squared plus 3, x, sorry. Right? Another one, f of x is 2x squared plus 3x minus 1. That's another one, right? F of x, big F of x is 2x squared plus 3x minus 8,429. That's another one, right? Because if we take the derivatives of any three of these, we still get back that little f of x. Okay, and that brings us to the first definition of the general form for an antiderivative, right? So let f of x, big F, let big F be an antiderivative of little f over an interval AB, right? Okay, then the function f of x plus c is also an antiderivative of f, okay? And moreover, if you find another g that is not equal to f, that is another antiderivative of little f over I, right? Then they must differ by a constant. Okay, this is why we can say it's the general form of an antiderivative. Okay, this is why we can say it's a general form of an antiderivative. That any antiderivative that we can find, we found, for example, the ones above, right? There were two antiderivatives that we were playing around with, right? But they differed by a constant. They differed by a plus c at the very end. That's the only difference between any antiderivative for any little function f. Okay. So for quick check one, I've got a couple of antiderivatives here, or I got a couple of little f's. Okay. I would tell you in try to do these in about 5 minutes, maybe 10 minutes. Okay. I haven't shown you guys really rules to find the antiderivatives for these yet, but I do want you to sort of give it a good faith effort and look at these and try to find the function big F that will give me the antiderivative for these little f's. As in, find me big F's, right? Find me functions big F such that if I take the derivative of those functions, I get these back. Okay. Again, just do the one that's assigned to you. Okay. And I'll look over solutions and I'll put them up in the notes a little later. Okay. So another definition, okay, is that of the indefinite integral. It's this thing right here. And this is essentially how we write out when we want to take the antiderivative of something, okay? So that means that this integral of f of x dx, we are referring to some antiderivative plus a constant value c, okay? A little bit of nomenclature about what the pieces are. The little f of x is what we call the integrand, okay? And the variable, in this case, how I've got it written up here, in this case, it's that x variable, x, is what we call the variable of integration. This becomes really important once you get to Calc 3, well, Calc 2 and Calc 3, Calc 3 for sure, okay? So yeah, all right. Here are some common indefinite integrals with the associated differentiation rules. Okay, so on the left-hand side is a bunch of your derivative rules that you guys must remember, right? And on the right is going to be sort of associated integrals, associated indefinite integral rules, so that we don't have to sit here and sort of semi-guess what the integral is, okay? So let me go through these differentiation rules really quick. We know that if you have a constant, you take the derivative of a constant value, that's always going to be equal to 0. The derivative of x to the n, you bring the n down minus 1 the exponent. The derivative of an ln is 1 over. 1 over whatever's inside the parentheses, right? The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared, and the derivative of e to the x is itself, okay? The one that I really want to point out is this one. Remember, when I covered this first, right, I did this thing. I did sine, cosine, and I did something along the lines of this. This is supposed to be an arrow, and then another arrow here, a plus and a minus, right? So that if you wanted to take the derivative, right, the derivative of sine is cosine, it's positive cosine. And then the derivative of cosine is minus sine. You guys remember that? Okay. This was just to keep your thoughts together when you're taking derivatives of sines and cosines, right? Okay. So now let's go ahead and do the integration rules that are on the right-hand side. If you have a constant, right? If you have a constant, then the integral of that constant is going to be k times x plus c. Okay, that's sort of the backwards between that one, right? Okay. Okay, so now let's get to the much more beefier ones, the nicer ones. Suppose you had the integral of x to the n, okay? Then the indefinite integral, or the antiderivative of something that looks like this, is going to be this right here. You do x to the n plus 1 divided by n plus 1. Okay? That's as simple as it gets, right? So just like the derivative rule, right, where you minus 1 to the x1 and bring the original down, right? This one, you plus 1 and then divide it by plus 1. Okay? The only exception in this case is going to be that n cannot equal -1. Okay, and the reason why it can't equal -1 is because of the rule below. Okay, that if you have, so if you recall, right, this is going to be integral of x to the -1 dx, right? Now, we want these to operate pretty much sort of inversely, right, from the derivative. And this is the reason why this one, the n equal -1, is the special rule, because the integral of 1 over x is ln, because the derivative of ln is equal to 1 over x. You guys see that? Okay. Next one down. Well, next two down, actually. I'm going to go next two down. The integral of cosine of x dx is sine of x plus c. So let's go ahead and let me show you what that means. So remember how I had this little picture right here, this little circle with the positive and negative for the cosine? All right. So this time we're starting, so remember the arrows is for the derivative, right? If you go backwards of the arrow, you get the integrals, the antiderivatives. So the antiderivative of cosine is sine, so that still works out. The integral of cosine is positive sine, right? And then same thing, right? Let's say you start at sine and you want to find the integral, right? That's going to be negative cosine of x. Ta-da. Okay. The next one down, that's basically pretty much sort of a backwards from the differentiation rule, the derivative rule. The derivative of tangent is secant squared, so therefore the derivative or the integral of secant squared has got to be tangent. Okay, and then the very last one, we know from what is that, chapter or section 3.9, 3.10, that the derivative of e to the x is itself. So therefore, the integral of e to the x must also be itself. Okay. So these are just a couple, okay, of the rules that we're going to be using. There's many more, many more. A more thorough and exhaustive listing of the derivatives and integrals is usually found either at the very front or the very back of a textbook. Okay, they're usually thick pieces of paper that sometimes you can tear out. Okay, I'm going to provide one for you. I'm going to put it in the course files. So if you go to files, there's going to be a nice big list there. Okay. You're more than welcome to print it out and use it and have it, stapled against your wall, up on the fridge, whatever you need it to do, so that you guys can sort of, look at it, have it as a reference. Okay. All right. So integration also has its own rules. Okay. We're going to pick up two basic ones for now. Okay. These two integrals are these two right here. The two rules are these two right here, this one and this one. So let me get to them really quick. So if you guys remember when we were doing derivatives, if you had an addition or a subtraction of two functions and you needed to take the derivative of them, right? Then what you could do was do the derivative of the first one, do the derivative of the second one separately, and then add or subtract whatever was between, right? Same rule applies for integrals. So let's say you had the integral of f of x plus or minus a g of x, right? Okay, then I can separate out the integral of f of x, do the integral of g of x, both of them separately, right? And then stick the plus or minus in between, right? And if big F and big G were the antiderivatives for little f and little g, respectively, then I can just put the plus or minus, whatever it was in between them, and call it a day. Of course, I still need to put the plus c, because these are families of functions, correct? There's, the antiderivative can differ by a constant. Okay. The next rule is just as similar as the one for the derivative, right? That if you had a constant times a function, right, you could just take the derivative of the constant, you could take the derivative of the function and then just tack along the constant afterwards, right? So same thing with the integral. Let's say you had to take the integral of k times a function, right? This means that I can pop out the k. I can pop out the constant value and just take the integral of the function itself and just take the antiderivative of f of x, little f of x. And if big F of x was that antiderivative, I get to just multiply the k to it and I'd be done. Okay, so how does this work out? Okay, so what I'm going to do is I'm going to do this example right here, and then you guys are going to be doing a quick check that sort of matches it pretty closely. Okay. Okay, so the first thing I'm going to do, and there's no shame in doing this, I'm going to rewrite it so I can get something a little nicer to integrate. Okay. So instead of having the square root of x, I'm going to do x to the 1/2 plus 1/2 x to the minus 1/2. This is some pre-calc stuff. If you can't recall your pre-calc, go back to your notes. Okay. So now I'm going to find the indefinite integral. So the integral, right, of f of x dx. Whoa. That is going to be equal to, right, the integral of x to the 1/2 plus this rewrite, right, 1/2 x to the minus 1/2 dx. Okay. I'm going to use the very first rule. This is an addition, right? So I can go ahead and split up these integrals separately, do them separately, right? So it's going to be the integral of x to the 1/2 dx plus the integral of 1/2 x to the negative 1/2 dx, okay? I'm not going to mess with the first one yet. So the integral of x to the 1/2 dx, I'm going to leave that one alone for now. But for the second one, 1/2 is a constant. So I can go ahead and do 1/2 times the integral, times the integral of x to the negative 1/2 dx. That's all I did. Okay. I only used the second rule from the one above, right? The constant rule, to just pop out the 1/2. That's it. That's all that happened. Okay. So now I'm going to go ahead and do the integral. So the first one that I'm going to do is this one. Okay. And according to the rule, right, that exponent is not equal to -1. So I can go ahead and do that power rule. So it's going to be x to the 1/2 plus 1 over 1/2 plus 1 plus, now I'm going to do this other integral back here. Okay. According to the rule, the 1/2 just gets to come along for the ride. The derivative or the integral for the second portion of that is going to be x to the -1/2 plus 1 over -1/2 plus 1. There's a multiplication in between there. Okay. Now I get to do this simple math here. So this is going to be x to the 3/2 over 3/2 plus 1. Whoa, let's make it bigger, huh? 1/2 x to the 1/2 over 1/2. Okay, I'm going to simplify this a little nicer. I'm going to get 2x to the 3/2 over 3 plus 1/2 times 2x to the 1/2. I'm going to cancel out these two right here. And I get left with 2x to the 3/2 over 3 plus x to the 1, x to the 1/2 plus c. And we are done. Here's our integral. Here is our antiderivative. Okay. So that means that if I take the derivative of this thing, I take the derivative of this thing, right? We know how to take the derivative of this thing. Then I should get this original thing back. So this right here is equal to my big F of x plus c. Okay. Simple enough, right? This is going to require some practice. So on your online homework, if you can, if you really need it, you should be able to request another problem and do that problem. It shouldn't reduce your grade anymore. So you can go back in there and just keep doing more and more practice if you need it. Okay. Okay. What comes up now is quick checks. Same idea. Okay. You're just taking integrals. Okay. Go ahead and write these out as best as you can. Okay. Now, let me go back to my example. This, as you guys can probably tell, and I've done this a couple times already throughout the class, this is really overly explained, okay? Because I need to show you guys sort of like the steps and the logic for every single bit, okay? Do you need to do this every time? Heck no, okay? So long as you show me a couple of these lines, so I'm thinking maybe starting with, if you do a rewrite, right? And then probably you guys are going to skip to this section, right? And then just give me this, right? That is perfectly fine, okay? As a matter of fact, once you get more and more practice, that's what's going to happen. You're going to start looking at this and you're, oh, this is going to be that and this and that. And then, oh, that's right. This is supposed to go quick after a little while, okay? So when you do these, right, provide some of the work. Don't be overly explanatory like I was, okay? And I'll check the answers and I'll provide solutions a little later, okay? So now I want to go ahead and show you guys something that will come up for most of you a little later when you continue on with your major, okay? So let's go ahead and continue this, consider this function right here. F of x is equal to x times x plus 2 times x minus 2. That is all reduced down to this thing right here, okay? So let's find the indefinite integral, okay? That is going to be basically, right, we need to do the indefinite integral. So the indefinite integral of f of x dx, that is integral, right, of x cubed minus 4x dx, okay? This is equivalent to the integral of x cubed dx minus the integral of 4x dx, okay? Again, I'm overly explaining this so that everybody can see the logic behind it, right? So then if I take the integral of x to the third, this is going to be x to the fourth over 4, right? Plus 4x squared over 2. And if I simplify that a little bit more, so this is going to be x to the fourth over 4 plus 2x squared plus c. This is our final answer for the antiderivative, right? Or the integral, the indefinite integral, okay? So what I want everybody to take a look at is this, that this over here on the, so you guys have a graph right there on the right-hand side. All of these are f of x's plus some constant c, okay? These are all antiderivatives of this function right here, okay? All of these are antiderivatives for that function little f of x, right? How would we find a particular antiderivative? So let's say, right? Let's say I am looking for this one right here. Let's say I'm looking for this blue one, this light blue one that's right there, right? How would I be able to, sorry, let's say I wanted to find the purple one. Let's say I wanted to find that purple one. How would we be able to find that purple one, right? They all differ by a constant, right? So how would we be able to find that purple one? And the answer there is we need a particular point. Right? So if you take a look at these graphs, and this is how derivatives actually really operate. Integrals, indefinite integrals really operate. All of these graphs, all of these, every single one of them, for any constant c that you plug in, they will run parallel to each other over and over and over. Okay. So the question still is, how do we find the particular one? We need a particular point, right? So if I want to find, let's say this purple one right here, right? Then I need a particular point that's on that graph in order to find the antiderivative that goes through that point, in order to find that exact purple one. So that's exactly what we're going to do here. I'm going to set what's called an initial condition of f of 0 being 2. So basically saying, I need the antiderivative that goes through this point right here, okay? Got it? We know what the general form of the antiderivative looks like. That's this one. Now we just need it to be going through a specific point. So I'm going to do this. So my f of x, my general form, is that x to the fourth over 4 plus 2x squared plus c, right? But we need f of 0 to be equal to 2. So then that means f, whoops, wrong f, big F of 0, 0 to the 0 to the fourth over 4 plus 2, 0 squared plus c has to equal 2. And this tells us that c has got to be equal to 2. So then therefore, our particular solution here, big F of x, the particular solution that runs through that point 0, 2, is going to be x to the fourth over 4 plus 2x squared plus 2. And we are done. Okay. So this brings up a really big portion of study in mathematics. It is the basic idea of a differential equation. Okay. A differential equation is an equation that relates an unknown family of functions to one or more of its derivatives. Okay. The simplest form is this right here. So we have a dy over dx is equal to a function in terms of x. Okay. This means that there's a rate of change, right? A dy over dx, a rate of change between two variables, y and x, and it is defined by a function solely in the variable x. Okay. A differential equation with an initial condition, okay, is an example of an initial value problem. Okay. And an initial value problem, those are really important in the study of mathematics, particularly in physics, in computer science, and in engineering, and yeah, basically everything, basically all the harder sciences. Okay. So to simplify, what's going to happen is this. A differential equation, right, is an equation that describes a family of functions like a script f, right, by its rate of change. Okay, so it's me. This is me trying to sort of explain it a little more. So let's say you had a differential equation that looks like this, right? That the rate of change between y and x, right, is defined by 3x squared plus 1. That describes the rate of change, right, of the family of functions, this right here. This is your family of functions, right? And if you take a look, that big F, right, is the general form of the antiderivative of this thing right here, right? Where c can be any constant value, right? If we want one in particular, right, then we need to specify an initial condition. We need to specify an initial point, okay? So what I want you guys to do here is to find the initial value problem that's been provided, okay? So I give you guys the little f, right? And I give you guys a point, right? Find the specific antiderivative that goes through that point, okay? So the idea of the antiderivative, and by extension, a differential equation, provides a really, really powerful tool when we need to extrapolate information from something that we have no idea how or where it's started. Okay, this is very common. Okay, so to show that, let me go ahead and show you guys this example right here. Okay. Let's say we had a rate of growth of a population of a dangerous bacteria, right? And we know that the rate of growth is this equation right here, right? And that's found by measurement. So we're able to measure and measure and measure and measure. And we find that this is how quickly it grows, okay? The PDT over time, so this is the population, right? The rate of change in the population over some time is given by this equation where T is the time, right? Okay, find the antiderivative, okay, and interpret what you found, okay? So what I'm gonna do first is find that antiderivative. So I need to do the antiderivative of 75 square root of T dt. Hey, hey. All dogs hate me. Bronx, get over here. He likes the scritches though. Okay. So to do this antiderivative, right, I'm going to follow the same rules. So it's going to be the 75 is a constant, integral of t to the 1/2 dt. So this is going to be 75 t to the 3/2 over 3/2, right, plus c. And if I clean this up a little bit, I get 50 t to the 3/2 plus c. Okay, what we did here, so look at what happened, okay? We were given a rate of change. Since the integral is sort of, or the antiderivative is operating as the inverse to the derivative, right? What we just found, right, is this P of t is equal to 50 t to the 3/2 plus c. This is our final answer here, and I'm going to interpret what I found in a second. Okay. This is the general form there we go. This is the general form for the population at time t. Okay. This is the general form for the population at time t. So if I wanted to find the population of this dangerous bacteria, all I've got to do, right, is plug in a t. Okay. But there's still a problem here in the sense that we still have a plus c at the end, right? That plus c has not been determined, right? So we still have a floating variable that we have no idea for yet. Okay. So that brings up part 2, part B. Okay. Let's say we have a very recent count that shows that after 2 days of observation, okay, the population has grown to 950 cells. Okay. How big was the initial population? And that's going to be our C, right? So what we're doing here is finding C. That's C at the very end of our P of T that's from part A, okay? This tells us that our P of 2 has to be equal to 950 cells, right? We get to now use this to solve for the C. So this means, right, P of T, let me actually just go ahead and do P of 2, right, is equal to 50, 2 to the 3/2 plus C has got to be equal to 950. Okay. 50, 2 to the 3/2 is 2.828 plus C is 950. 141.42 plus C has to be equal to 950. This means C is equal to 808.58, right? So the initial population of bacteria was 808.58 cells, right? So we can go ahead and comfortably say that the initial population was somewhere around 808, 809 cells, right? So that means P of T is equal to 50 times T to the 3 halves plus 808.58. This is sort of our final equation that models the growth of this bacteria, right? But to answer the question, right, how big was the initial population? 808, 809 cells. Okay. So now I want everybody to take a look at what this did really, what really happened here, right? Look at what we were able to do, right? By measurement, we're able to determine how much or how fast this bacteria is growing, right? We didn't have to be at the very inception of this growth. Does that make sense? We didn't have to be at the very beginning of this dangerous bacteria. We just needed, look at what's happening, right? We just needed how quickly it was growing, right? And a point much later. And specifically, we just needed the point that after 2 days of observation, 950 cells were present. From those two things alone, we were able to sort of reverse engineer an equation that modeled the growth, right? And moreover, it gave us the initial population. So this is why this kind of work, this study in mathematics, differential equations, is so important. There's lots of research that's being done in how to solve these differential equations. Okay, this is the pretty cool stuff. Okay, all right. Besides that, the next thing that comes up is lecture questions. So if you guys have any questions about this material, I've got my drop-in Zoom hours and my lab hours from 3 to 6 p.m. every day, Monday through Thursday. So just drop in, send me an email, send me a discussion post, whatever, however you can get a hold of me, okay? Besides that, study hard. I'll see you guys around.